Give me 1 minute. All right, so let's go ahead and get started here. So first of all, I'd like to welcome you all and thank you all for coming. We're really excited for our CUSP seminar series for this semester. We have what I think is going to be a great set of talks and a lot of opportunity for us to engage as a center. I also want to start by welcoming Jackie Libby, who is a new Smart Cities postdoc with us, and will also be co-organizing the seminar series with me this semester. So you will be hearing from both of us throughout, and yeah, hopefully we will, sooner than later have a chance to be in person one day as well. With that, I'm actually going to pass it to Farouk to introduce our speaker for today, and we're really looking forward to it. Farouk.
Thank you so much, John, and thank you everyone for being here today. So it's my pleasure to introduce to you Golnaz. So I knew Golnaz when I was doing my undergrad studies. We went to the same school and we worked in the same research lab, and I had the pleasure of working with her, and we had a robotic project at the time, and so we continue being in touch, and Golnaz continued being a very successful researcher and scientist. So again, it's my pleasure to introduce to everyone Golnaz Habibi, who is currently a research scientist at the Department of Astronautics at MIT. She will join the Department of Computer Science at the University of Oklahoma as an assistant professor in 2022. So congratulations to her for starting this great position. And previously, she was a robotics engineer at Auto Robotics, leading the team of motion planning of autonomous drones. Golnaz's work lies at the intersection of robotics control, machine learning, and multi-agent systems. Her current research focuses on visual autonomous navigation, reliable communication, and improving the safety and reliability of autonomous agents. And the title of her talk is Safe and Resilient Autonomous Driving in Smart Cities. So with that being said, I would like to invite Golnaz to take it from here. Golnaz, the stage is yours. Golnaz, you're muted if you...
Can you hear now?
Yes, we do hear you.
Okay, cool. Yeah, I think we have multiple systems. I wasn't sure which one is working now. So cool. Thanks so much, Farah, for inviting me to this wonderful robotics seminars in CUSP. And it's my pleasure to present my work during the time I was at MIT as well as Rice University during my PhD, and also what would be like the next step of my research during the time I will be at University of Oklahoma. So today I'm going to talk about the safe and resilient autonomous driving in the smart cities. So you see that this figure here, and actually smart cities can have many meanings, and different smart and intelligent components would be in smart cities, but we are more interested in the part of the smart mobility in this here. So more like focusing of this talk more on the autonomous driving system. So I start my talk with some like advances in robotics today. So we know that the robotics has a lot of advantages today in different applications. For example, you see that, for example, the robotics at medical services, and also for the saving the people, as well as, for example, autonomous driving systems. For example, here was like one of the videos from Waymo, autonomous cars. And it can be other areas application, for example, for entertaining. For example, Intel here using for like and showing the demo of the multi-agent systems, as well as Skydio as one of the famous drone system and flying robot system. And as well as also we can see that the service, so for example, Kiva, Amazon, or also Boston Dynamics are very popular today, is that they have all these services to the people and in different kind of applications. But however, and numerous challenges we still have with the robotic system. One of them is that in general is that why our system of the robotics, we try to make it like be in real life, but it still is isolated in labs or maybe just a specific setup and experiments. So I categorize in 3 different challenges that we have now for the robotic system and AI. So one of them is like a transferability and a scalability. So we more want to have the robot to be adaptive to environment, task, and challenge and task changes. So an environment changes. For example, we have robotic here, so we know that it's worked properly in one environment, but how we want to move it to the other environment, for example, to the outer space and underground. So how we can have the system be reliable in that new environment, and also robustness. So today we deal with the adversarial attacks and uncertainty in the environment. So how we can have we can robustify the system to be robust. For example, here you see that the adversarial attack and adversarial patch, for example, for human, it's be easy to see that this as like a stop sign, but adding this, it's changing to for the neural network to be more sensitive to this adversarial attack and using that, consider as it like a different sign. And of course, the interactability. We want to have robots live with us and work with us. So we want to have a high interaction between the human and robotic system. And as well as robotic grows, we want to have a connection of the robotic system. In general, should be heterogeneous system. So this is one of the examples that's showing that the connectivity between the other cars in the connected robotic system or connected cars, which is important. So all these 3 majors of our challenge that we want to address in this talk. So the first one is this robustness as certification. So there are many advances in neural networks and learning-based method, and we have a very efficient algorithmic and robotics in this area, but we have a lack of the robustness in general for neural network. In presence of the adversarial attack, recently they more focus on that this direction of the research. For example, here that you see that this is like the image that if you add some specific noises to the system in the computer vision, for example, the system can not detect it as a panda. Even for the human, it'd be easy to understand it. And also the other one that I just explained to you before that is a stop sign change to the other sign for the like a speed sign. So this type of the like uncertainty and adversarial behavior and several attack can actually falsify the robotics system or in general neural network. And also usually our area that we train our model would be different from the area that we tested. So having a different data distribution during the testing and training would make the system not robust in our in real world. So and the other thing that in many cases it's not safe to use the robotic system in real environment for the training. So we use a simulation. So how we can have a good transferability from simulation to real world. And of course, the safety and critical domains. So here, these are one videos from our lab that we show that there's a social aware navigation system. So this robot successfully will navigate in one of the like building in CSL area for the at MIT. But the problem is that if you want to move this robot, for example, to this area, that is one of the picture from the subterranean DARPA. Actually, it's happening now. A very interesting challenge. So how we can actually have the robot to be working in areas that we don't, for example, not very like simplified version, so we can work it on this and robustify the system in this type of an environment underneath or the areas that there is no GPS or Wi-Fi, and how we can like have a good model of the environment and navigate safely. And of course, the other thing is like very important in the safety of the robotic system. For example, in autonomous driving, we know all the mistakes by the self-driving companies like Uber or Tesla that led to tragical crashes. And also, for example, here this video is showing that having like a very small patches on the road, it makes the system full, and the system thought that is like a big like obstacle, and it changed the direction, and it would be unsafe during the navigation, both for the pedestrian and also for the passenger of the car. So we want to see that how we can have the model, the tool can measure this robustness of the system, because we know that our model would not be very robust in all the situations, but the question is that how we can measure this robustness so we can have a more crucial and more conservative behavior based on our neural network uncertainty. So the work that we work on it is like here based on the like a closed loop system. So, and for example, you have the robotic system here, and then we want to see that, for example, this drone, if can like avoid this obstacle as avoid set, and however it can reach the goal set. So this is actually the certification problem and verification of the system. So how we can have a system if it's trained by neural network, so the control is based on neural network, but how we can guarantee that our in presence of the uncertainty, we achieve the goal and we avoid the obstacles. So, and in general, we have a neural network, we have the input and output to the network, and then assume that the input would be some interval or some uncertainty in input. So there's not just one point. So by having that, how we can create or measure the output of the system, so uncertainty on the output, and based on that, we can make a more safe and more efficient decision. So that's the whole idea. But the problem is that it's usually the neural network is nonlinear, and it creates a very complicated output, the real output. And our goal is to approximate this boundary, for example, by using finding this bounding box of this area. So that's the goal. And in general, finding the exact this neural network output, as I said, very challenging, and there are many work in that area. So it's between like we have between the trade-off between the efficiency, time efficiency, and finding the exact output. So for example, a STP model based on the semi-definite programming would be very exact, but it takes time. But linear programming on the other side would be not as exact as the STP, but it should be faster. So our work is really some split in between these two. So we try to trade off between these two factors. So so the idea that we have, we do we combine the neural network relaxations with this, some partitions. And the idea here, I show that is like output, we do the for the input that can have some uncertainty from the sensor noise or the adversarial attack. So by having that, instead of having feeding all the set of the net and the input to the network, we want to we partition it and send each partition to our tool for the measuring the output, and the output, the total output would be the union of that. So this is our network. For example, it can be like a robotics control system, and then we can use our model we call the greedy sim guided method. So it shows that we try to like optimize that, refine this black line as our approximation to be as close as the red line as our ground truth as our output of the system. So that's the goal, and we show that by having this partition, we can have a much tighter boundary around the approximation of the output. So, and in general, so if we want to also have this model and using that for the robustify the planning. So for example, one of the application is a collision avoidance. So I show here the video. So, I'm sorry. And in the previous work that we had before in our lab, the blue, I mean, I explain here that the blue one is our adversarial robot or adversarial agent that wants to attack the red one. So the red one tries to avoid that blue one. But the problem is that the blue one doesn't have, and we don't know about the exact the position of the blue. There is some uncertainty on that blue one. So based on that, for the previous algorithm that we had, it has very conservative behavior. You see that it tries to deviate the object. So of course, it doesn't collide with the blue one. But in our new approach, because we add this partitioning part, we improve it based on that, and we can approximate the output of the system or the behavior of the blue one with a tighter boundaries. So we don't need to deviate or change our direction so much. So we see that how much we improved our efficiency. So it still is safe, but it's more efficient in terms of reaching the goal and having the shorter path. So we show that like 22% also faster time to goal we have it when we use this algorithm. So any questions so far? Okay, so I go to the next part of the topic is next part of this talk, which is the topic is transferability and lifeline learning. It's very important because again, for the smart cities and this type of the environments, the environment is going to be changing a lot, even in the different times of the day would be different. So all of this making like sense that we have a model that will be transferable and we can also continually learning the model. So most specifically, the challenge that we have that is most of the training-based model or learning-based model is like task-specific and not generalizable to new domain. So we want to do the like transfer learning, so we can transfer our knowledge across different tasks or environments, as well as we do the continual learning. So we also how we can continually learn when we explore new environment or tasks. So we cover that mostly on the transfer learning and continual learning of the motion behaviors, especially for the pedestrians, which is, I think, is one of the important components in the self-driving cars. And we also showing that how we can also learn and continually in this domain. Here's actually showing that this video that despite a lot of progress in object tracking, we have actually the problem of the inferring the intention of the pedestrians. And so the problem, because we have very high uncertainty in the pedestrian motion and the direction, so and also the pedestrian usually show the hidden intent, so we don't know about what's exactly they want to where they want to go, or they abruptly change the direction. So, and also they have very high interaction with the industry in the environment and the other pedestrians. So having all this and modeling all these factors is challenging. So for example, in the environment like this here, that like we have a crossing road area and a lot of interaction between the cars and the pedestrians. So it's important how we can find a good model and find a good contextual feature. So the context we use from the environment is actually traffic lights, and also the location of the crosswalk and intersection geometry. We want to use that because we know that this is it influences on the pedestrian behavior. And pedestrians usually also violate their rules, not usually, sorry, sometimes we violate their rules. So for example, jaywalking, so it makes it more difficult compared to like the cars and estimating the cars' behavior. So the idea, as I said, we want to have it still grasp that type of the context from the environment and using our learning model. But also we want to have these features to be transferable. So if we learn in one environment, we can transfer it and use in another environment. You see that in many like work so far, for example, they train on one specific data set, but if they want to transfer it in another data set, it's not working well because of that transferability issue. So the idea that we have is mostly we focus on the intersections, because the intersections is one of the areas that we have a lot of high interaction between the pedestrian cars and the pedestrians as well. So we want to use that context that is distance to the curbside as well as a pedestrian traffic light. And the model that we show that here is basically instead of measuring the distance to this is assume that this is the intersection corner, instead of measuring the distance to the curbside and the orthogonal distance, we use this specific distance that it is called contravariant distance, and using that we can having a transferable model. So such that if you have, for example, trajectories here, the red one and the purple one, we know that these are in the shape is very different in the like geometric view. But if we use this transferable tool, we can transfer it in the same shape, and so both of them represent the same intent, which is turning left at the intersections. And that's our idea, and this is very useful because now we can have our data sets, and then we process on all data sets, and then we have the new and uniform domain for our data to train on. So our contribution that we basically we use this model, and then we actually first of all it can be transferable from one intersection to another intersection, but also we are interested to use it for the continual learning. So most of the current algorithm is basically based on the offline learning. It means that we cannot train during the time that we test or explore in the environment. So having that said, that our contribution is to incremental learning the model. So we use the sparse coding application tool for that. So just as summarizing that, the transferable learning that I said, if you have a data set here, we use that transferable learning that at first we transfer it to the new domain, which is like that transferable domain that I just explained to you. And then based on that, we have the set of the motion primitives and their transitions. And we learned this that so that the trajectories are now kind of the clustered as a motion primitives. So now assume that now we have a new data set is coming in another time, or the robots or the self-driving cars move to another location, and then at time t1 we want to just we want to modify the model. We don't want to just train just this specific batch of the data. Now we just learn on the specific batch of the data it just arrived, and then we want to fuse this to model M1, M and M prime. And for having that, then now we fuse this to model. And for fusion of the model, we use a specific graph, the motion graph, and we fuse it based on the similarity between these motion primitives. So we have some tool, the tool that we measure this similarity, and then similarity score. If this similarity score is higher than some threshold, we fuse it. Otherwise, we consider as a new behavior and add it to our model. So having that, so now we have a new graphical model, and then we can use this model continuously for new data sets, and we can just continually learning from the new batches of the data is coming. So this is a result that we show here. We use it, we have like 8 intersections actually, and here I show the five of them. So we collected data with different tools. This one is for one of those data platforms, collection platform. We have 6 cameras and 1 Velodyne on top of it. And we fuse all these data sets, and then it shows that we have like we did it around the MIT campus as well as the Boston area. So you saw that we have like we feed the data sets in from 4 different intersections. The error of the prediction, which is one of the like popular one, is that basically the average distance and displacement error. It shows that it's decreasing. So it's showing that our model trained continually as the new data sets is available. And by the way, the testing area is completely different from the testing training environment. And interestingly, that our algorithm is working when the intersection has different geometry. For example, some of them is orthogonal, but some of them is like they have different angles. So, and then we show that in a testing there with completely different intersection and geometry, we were able to learn the model. And also we tested with the available data sets. The blue one is our model, and the yellow the ground truth, and the green one is the observed trajectory. So we predicted the other part of the trajectory, the future part of the trajectory, and it shows that our model is the closest one to the and compared to the baseline. So we also continue this work because we want to have it for the fleet of the vehicles, how we can also share our learning model. So we don't have to each car learns by itself. So that's the framework that we have. So we extend our work for the multi-fusion. So each car can learn by itself, but then it can share its model either by other car by in the center node, and then we can each robot can or each car can leverage the learning model from others. So that's the whole idea. So I don't go to the detail, but it's most of the collaborate and the contribution of this work to how we can fuse multiple model efficiently such that we still have a good size of the model and in real time. So I go to the last one actually in the challenges. So I'm not sure how many minutes I have time.
So we're here till 1, but we try to have some time for discussion. So maybe another 15 minutes, if that works for you.
Yeah, what time is it now? I gotta use my cell phone.
12:31, sorry.
12:30, okay.
Yeah.
Okay, cool. Okay, so I will try to be fast for this last and the next. There's some actually, I don't know the question or okay, I just checked it. Okay, cool. So the last challenge that we want to talk about the interactability and multi-agent system, and it's more focused on the robotics search and rescue, which was one of the important topic in robotics area that that can save a lot of human lives. So okay, so I already started with that about the motivation this work. So the single agent, it shows that we have a lot of great advantages in the different applications. And we show that but it involves the interaction between the multiple agent when we want to have it interaction between the multiple agents. And in some of the examples here, so the robotic soccer or robotics for the building and construction, and also different other application that I explain now is like robotics search and rescue. And here you see that what we do actually be inspired by animals like the ants, the insects, that they have collaborations, but they are very simple. So they use very simple communication system to communicate, and as well as to share their information, and also do some tasks that individually they cannot do it. And it's useful using this method that because the necessity of the human-robot interactions are other part for the self-driving cars and service robots, not just the communication between the robotic system, also between the human and robot system. So the key challenge here is the scalability. So how many robots that we can involve in that multi-agent systems, and also in general. So because we have a non-stationary, we have actually non-stationarity when we simultaneously learn. So because they are simultaneously learning, so we have this behavior. I don't go into the detail of that, but this is a very big challenge here. So and other thing is that having a good communication. So who and what to communicate. In general, multi-agent can be in the centralized and decentralized. This work is focused on the decentralized algorithms. So the idea is that using this model for the robotic search and rescue, and I just go very quickly about that. So our assumption is that we have a local communication and positionings, and we have a decentralized execution and action. So it starts with the exploration here. So the robot explore the environment. So for example, they explored some areas that without any GPS or Wi-Fi. So they use just local communication. They use just infrared sensors for measuring the distance as well as the communication. And then after they cover the environment, so we have a net of the robotic system is a connected network, so they can create a network. And then they found the object, for example, and then they attach the object. So you see that here, this robotic with a specific gripper design, they can come and attach the object and grasp it. And then when you grasp the object, it can measure the centroid of the object as well as dimension of the object. And by using that, we can create a path and have a motion planning, because the goal is that we want to move this object. For example, assume that it's a human survivor. We want to and some injuries from the like earthquake or the other like disaster areas, and we want to help to collectively transport this object. And safely, of course. And then we create these trajectories and based on from the robotic systems, and then we want to move and navigate it. So we use all this decentralized. So we navigate this, navigate the object and transfer this object to the safe environment. So that's the whole idea. All these are like a decentralized. I go just quick about a structure of the robotics. We designed this robotic system at Rice University. It has like 8 transmitter and receivers, and they use the infrared sensors for the bearing and orientation and distance measurement. And robots have 2 different set of the categories, like manipulator robots that transfer object, and the guide robots that they find a path and then remove the object. So I'm not going to actually now go to the detail, just very briefly that showing that the idea is that we have this set of the guide robots that cover the environment, a sample environment, similar to the sampling-based motion planning, but now we sample the environment by the robotic system. And then after that, the goal is that it's just showing that here's the obstacles, and then this is the object of the robot. And when we have the dimension of the object, but that we can measure it again in the decentralized fashion, then the output would be that basically based on the dimension of the object, we can estimate and find the best path and safe path through this object and this environment. So we create this path. So we have different colors of the path and the robotic system. So if it's green, it means that this area is safe for the object to be there. So object can be in any orientation. But the gray one is the areas that just the object should be in the specific orientation to be safe. So for example, we cannot rotate the object in these areas, and just a red line showing that the safe orientation of the object. And the unsafe areas is the white robotic area. So the robots that say unsafe, it means that the object could not be in this area. So by having that and using a distributed algorithm based on the Bellman-Ford algorithm, similar to the digestor, but in a distributed fashion, we can find the shortest path. And also we have a specific navigation. So I'm not going to the detail of that, but it's basically based on the like safing and unsafe and safe minor, which is like a specific direction, which is safe. We navigate from one node to another node. So the whole idea I come back here is that when after the path is generated, we want to move the object from one node to another node, which is a robot, and each robot shows that if that position is safe minor or safe, and then basically based on that we can navigate from one node to another node. And use the combination of the rotation and translation. So there are more details here that how we can use it, but basically we have like, for example, we measure in the middle, we measure the center of the object or estimate the centroid of the object, and then basically we rotate the object around that point. And then for the rotation, and we can do like using like flocking approach for being the same orientation and move. So I just showing the video, just a simplicity. So you see that here, the robots cover the environment, attach the object, and then after we attach the object, we cover the environment, and then the robots are specified based on the distance to the closest obstacle as a green, which is safe, unsafe is white one, and the gray one as a safe minor. And by having that, so the robots, only the robots that which is safe or safe minor, they attend in the path. So then we create this tree of the robots from the origin from the goal position, and then we find the shortest path on it. And then after having that, now the object, the robot around the object are I don't know, some issue with the video is I think the Zoom thing, but anyhow, so they try to like move the object to when they guiding by, and they are guided by the guide robots. And here just a video that we show that here. Actually, we try to like, and this is our goal, that finally we want to move the object, which is a human, in the environment that there is no GPS and Wi-Fi, and just the robot can go there. So we have a set of the robot that they attach the object and pull the object and move the object in the environment. So the blue robots are specified as a guidance, and they can guide the manipulator robots to move the object. So we have all this for exploration, attachment, and then perception, and then path planning and navigation. So this is showing that all this, the algorithm is like end-to-end collective transport and end-to-end actually distributed. And so I'm going to skip this part. So this is also another thing that in terms of the robotic interaction, our goal is to showing that this is one work with the University of Washington that we did. So for the having multi-agents reinforcement learning area. So the goal is that the robot on the right side try to protect the ball, and this is an attacker on the other right side. So the robot is a defender on the right side. It tries to avoid the robot on the left side to attack the ball. And it's actually one of the first work actually in this direction, that they use the reinforcement learning specifically for the multi-agent systems in physical game. And we are working on this for improving this idea. And I'm just showing the video here in the matter of time. So showing that here, that how actually is played this game. And this is actually kind of the virtual ball. So at the beginning, the participant trained that where should be the ball. And then because Candy was pretty suspended there, and it tries that the human is an attacker, tries to attack the ball, but the robot protected. And we played, and for example, this human didn't play very well, but we see that we have some. I show the last one actually that plays the best one and get the highest score. And it goes like 1037 versus the other one minus 137. Okay. Today I talk about the different challenges in the autonomous systems, specifically the autonomous driving system, and then I extended to some other applications. So mostly focus on the communication, transferability, and adaptability. So we want to bring the robotic system to the AI and AI in real world, specifically in smart cities. But there's still a lot of challenges. So that's the question is about is next. So the technologies as technologies mature, transition and deployment into real world environment scenarios will be challenging. So we still see challenges in the area of the trust, verification, and explainability, especially for neural network, which is one of the powerful tools that we use now. So we still work on that. There's so many work that they try to improve all these factors, but we still need to improve other factors. One of them is cost of the artificial intelligence. Many of these systems that it needs a lot of sensing equipment, like for example lidars or cameras, but cameras much cheaper. So the question is that how we can reduce, for example, lidar that I explained in the next slide. And also the safety and resilience. So actually here, for example, it's very important that you predict the pedestrian and track it, how you can have a safe model that if you train in one environment, you can also plan effectively in other environments. So safety and resilience of the robotic human environment and interaction is very important. And also having adaptive interaction and learning, and that's the other factor. And of course, as we grow that the robotic system, we need to have a focus on the heterogeneous multi-agent system. Most of the work that I showed so far is like more homogeneous multi-agent systems, but the question is that if you have a different kind of the robot, how they can interact and communicate, and in general having a scalable model. And of course, we want to have a robot to be like this. We still not reach that point that have a robot to work together with the human side by side. And also other point is like about the robustness in the different situation and transferability, for example, different weather conditions for the autonomous driving system, as you see here. So it's still a long way to go there. One of the work that I'm working on is that they try to use the low-cost autonomous navigation systems. So I focus on that. The previous one is that this is the video that we had it before, based on the LiDAR base, and instead of the LiDAR or the camera. But our goal is that how we can have it, the system, just the camera. So you see that I have 3D LiDAR and RGBD. So and you see that, for example, it tries this robot to avoid the pedestrian, but our goal is to have it this system exactly, but by having just the vision. So we have it at low cost and having a robotic system for everyone. So that's a thing that we want to have the vision to be employed all this perception and planning and control side. So I think there's a video here, but it's not playing now for some reason. Anyhow, so there is like also some current work that we are working on it based on a monocular 3D object tracking system. So we are still working on that areas, and to see and improve the model. So this actually end of my talk. Just one last slide as I mentioned, I'm going to join University of Oklahoma in next year. So actually we are growing, and if you're interested, join our lab as a PhD undergrad and graduate student. So for the different project that we're working on there, I will continue all this work during my time there. So more focus on the self-driving cars, machine learning, reinforcement learning, and multi-agent systems and autonomous drones. And yeah, so that's all. And also this work couldn't be done without all this collaboration with very great people here, just some of them. But that was a great opportunity for me to work with them. So, and if you are more interested in our lab at MIT, please visit our YouTube channel, and I'll be happy to take any question. Thank you.
Thank you so much, Golnaz. It was a great talk, and I personally enjoyed it very much. So a lot of amazing work. It was absolutely impressive. So yeah, so maybe I would like to open this stage for questions from the audience.
I have a question.
Yes, Jackie, go ahead.
Okay, yeah, wonderful talk. It's just wonderful work you're doing, and I just really appreciated how clearly and effectively you communicated it all. I had a specific question about one of the first projects you mentioned, having to do with the estimating the distances from sidewalks and those curves you were showing. And you were getting that from the Velodyne data, is that correct?
Actually, it's both the Velodyne and the camera. One of them, I mean, it's a combination. Some of them just a Velodyne. So let me.
Okay.
Yeah, you have just to go. I pronounced it this.
Yeah. It's good to go to the slide. And then my question was, it seemed so. right now you kind of have to, like you show in your field testing photo, you kind of have to be there with this expensive equipment at every intersection in order to collect that data. But in order for this to be used in the real world, you would ideally want every intersection in the world already modeled. And so what will it take to get that? What needs to be done? Like right now with satellite imagery, is that enough? Or do we need self-driving cars that have traversed through the world with Velodynes on them to have previously seen them in order to have models for any intersection that you would be like going towards? Like, how do you see this being used in the real world, and how close are we to getting there?
I see. That's a good question. I mean, there are two aspects from the modeling the intersection. One of them that's modeling the intersection in terms of like mapping and finding like the geometry of the intersection. There's actually, we also use like a Google Map for like finding exact dimension, but also we have the RDR map that we fuse it with that. But for the terms of the capturing the pedestrian behaviors, we still need that the image from the camera point of the, the point of the view of the robot, because later on we want to train on this model to be like assume that the robot's in an intersection, and then based on what it's learned, it can react or at first track the pedestrian or the other cars and then plan accordingly. So we need to have it actually, the data set to be from that point of the view. That's very important to having also the images. Yeah.
And so okay, so you need it coming from the point of view of the robot. So do you think that once self-driving cars become more pervasive and they're collecting this data over time, that eventually you'll just have enough data from those self-driving cars driving around with Velodynes in order to have enough data? Like, is that the kind of vision that you see in terms of being able to have data for some random intersection that you?
Two things. One of them, that approach that I showed is not a neural network, so actually just a classical machine learning. So the one that the transferable model. So that model showed that even if you don't use a neural network, we use a classical machine learning method, by having transferable model of the trajectory, you can transfer from one intersection to another intersection. But the point is that in general, you know that the neural network, general machine learning, data-driven approaches are data hungry. So if you have you want to have a good model to be generalizable, of course, adding more data set as much as you can and train based on that, definitely useful. So, and that's why that maybe it's not possible one car can train all the data sets. That's the other part that we work on it to sharing this knowledge. So if, for example, a set of the car already model the pedestrian behavior, how we can share this knowledge with the other cars, and having like a more scalable and compact and compressed way of this sharing is also important that we consider that. Right?
Very cool. Yeah, thank you.
Thank you so much. I think there's a question from the audience. Yeah, Magdalena.
Yeah, thank you. Hi, first of all, thanks for that fantastic talk and fantastic work, really. I have a more like a general or high level question. My background is more audio. And as you were talking and like you were showing the type of AI systems that are being developed for tracking what's going on in urban settings, it's heavily based in computer vision. How you track pedestrian, how you track other cars. So my question is, what's the state of audiovisual research in this, in autonomous driving? What are the perspectives? What are people looking at?
Yeah, that's good, very good question. And the one thing is that mainly most of the work in this area is heavily based on the LiDAR-based, or the combination of LiDAR and vision. So that's the thing that still we have a large gap between the LiDAR and the camera-based models. So one thing that we want to try to have it still have a key camera that, but still have a good model. So, and the other problem that in general for the pedestrian, specifically the tracking and the occlusion is still, that's a big issue. So many algorithms still working fine for the, like when we have a sparse environment, but for the highly dynamic environment with a lot of pedestrian, with a lot of occlusion, it's really hard. So still people work on that because, you know, we want to have this self-driving car not be isolated. Just not, we don't want to run it in the like highway areas. We want to like run at intersections, like New York City, like and Boston areas, like cities in China. So like it's very important to consider these realistic situations that we have a lot of interaction and occlusion, but still none of this algorithm, I should say that. Answer, for example, nuisance data sets is one of the large data sets, but many algorithms that shows that, for example, very good performance maps in kitty data sets, they fail on nuisance or VAMO data sets, which is more realistic data sets to the real, more realistic data set, I should say, yeah.
Yeah, because like the examples you were mentioning that basically weather conditions for lighting, or I don't know what's going on, like when things are happening, cars approaching or things like that, is something that you can get clues from the audio. And I was just wondering if people were looking into that.
That'd be great. So yeah, that's a very good idea. I see that not in this tracking. I see that tracking in the like indoor environment. They use like the combination of the audio and the especially for the detection of the presence of somebody, more in the security case, that they consider that audio processing with the images. But I think that would be great, specifically I think in the areas that, as you mentioned, that because of the weather or partial visibility, at least we can, for example, for the safety part, if we can, as I have this part that it gives some warning if it cannot detect anything, but it can hear something, for example, it can warning. Yeah, that'd be a good idea.
Thank you.
Thank you.
Okay, perfect. Any other question from the audience?
I have a question. So thank you so much for the talk. Really amazing work. Towards the later part, when you were showing these demos of the collective transportation demos, in a lot of those scenarios, you seem to assume that the space is static, right? Like the geometry of the space is static. What happens if you have dynamic changes, right? Like, I mean, for instance, the example that you show seemed like some sort of a recreation of an emergency response scenario, but there you could have things falling or moving. And so what is the state of dealing with those, you know, dynamically changing spaces? And yeah, just curious to hear your thoughts on that.
Sure. Cool. Yeah, that one is, we have some, I mean, that system may be kind of instant reaction to the movement. So we still have that high and dynamic environment that the guidance robot, they try to like, when they clear the path and move away, but yeah, we have not very much like complicated scenarios in this term, but most of the work now is more focused on the reinforcement learning. So they try to use the reinforcement learning to get a much, plan a much more safer action and a more optimal action based on that. So this work that I done was not actually even is not machine learning type. It's just more focused on the communication and decentralized algorithm. But for that part of that challenge that you mentioned, most of the work focus on using the multi-agent reinforcement learning. And so we can make a decision, these scenarios that we can have optimal policy, design optimal policy to, for example, avoid the collision, and also even they estimate the policy of the other agent in the kind of the multi-agent setting, or they even like they model it as like a game based on the game theory. So the one that I showed at the end, that this robot and the manipulator robots and the human are playing together, is basically type of the multi-agent reinforcement learning. But of course, we have to consider not just these two robots and robot and human and multiple systems. So we have some work like CADRL. It's not my work, but from our lab. So CADRL or GoMPC, this very great work that graduate student and postdoc that did in our lab. So basically that one. So it's showing that collision avoidance of the robotic in the environment, that we have a highly dynamic environment. Actually, the video I showed that at the end is basically doing that. So this one here is basically this multi-agent reinforcement.
Okay, thank you.
Okay. Thank you so much. And I would like to also thank Jackie and John and for organizing these talks, and thanks for letting me to introduce Golnaz, and thank you, Golnaz, for being here today. It was a great pleasure having you, and at the maximum, I think we hit to near to 40-45 audience, if I'm not wrong. So that was a great talk, and it was very interesting. I'm sure students and researchers, they liked it a lot. So yeah, so just want to appreciate your time, and thanks for joining us here.
Yeah, thank you so much, Farrokh, again for inviting me, and it was my pleasure to be here with you. Thank you. Have a great day, everyone.
Great. Have a good one. Bye-bye.
Thanks, everyone. We'll see you next week.
Bye.